Hi, my name's Liz. I'm a software engineering manager on the switching team at Cisco Meraki. Prior to Meraki, I worked in startups ranging from Series A to IPO. I lived in Ohio for 24 years, so I'm no stranger to the 5-hour road trip to see a show in Chicago. I truly think Chicago is one of the most perfect cities in the world. I have a friend who calls the Great Lakes the North Coast of the US, and I love that description. I think that's so fun. Believe it or not, people, not me, do surf in Lake Michigan during storms. Often in the winter, it's very gnarly, hence why I've never done it. So hopefully the surf theme of this presentation is fitting enough for the nautical town of Chicago. This talk is primarily about time series data. Time series is a topic that Cisco Meraki deals with quite often, and it can get really intricate and hairy. I've found that the gotchas can be quite difficult to uncover at first, so hopefully this presentation helps anyone who's currently finding themselves daunted by the concept. By the end of this talk, you'll hopefully have an understanding of how time series data might differ from the typical sort of relational data you might be used to dealing with. I'll walk through how to select a tool for managing time series data, how to organize time series data, how to query time series data, how to aggregate and compress time series data, and finally, how to translate your design to API constraints. Before jumping in, you might be asking yourself, what even is time series data? Time series data is essentially just a collection of observations recorded over consistent intervals of time. Time series data is distinct from other types of data because of this ordering by time. This graph, lifted from our dashboard at Cisco Meraki, shows a usage rate in bits per second for a device over time. We record this data every 5 minutes by polling the device, we store it in a time series database, and we display it to the user in a graph on our dashboard. Time series data has become pretty ubiquitous as we collect more and more data to model our surroundings and predict trends. Devices like smartwatches have introduced amateur athletes to way more data than they've ever had access to. Our friend Liz, inspired by apps like Strava, wants to track her surfing as well. Liz has just taken her first surf lesson, and she's keen on learning how her surfing will improve over time. She's decided to record this data in a time series database and to access it via an API endpoint. But where does she start? In surfing, it's important to select a surfboard that's suited for a particular swell. If the waves are steep and powerful, it might be worth breaking out the shortboard for better maneuverability. For smaller days, a longboard can be a lot of fun. I've recently been told that it's absurd that my partner and I have 9 surfboards between the two of us, but it's important to have a lot of options. Conditions really do vary. The same is true of data and databases. It's important to select a tool that's appropriate for the type of data you plan to deal with. Time series data often comes in large quantities, and efficient access is highly important, so a database that can accommodate these concerns is crucial. When selecting a tool for managing time series data, you have 4 options that nicely mirror the options a surfer faces when deciding what board to surf. As a surfer, you can surf a board you already have. This is applicable for folks who already have a dedicated time series database in their tech stack. As a surfer, you can use an old board but add a new set of fins. This is analogous to using a database extension for, say, Postgres, adding on to a tool you already have. As a surfer, you can buy a new board. This is similar to adopting a new database technology dedicated to time series data. Or you can break out the foam and fiberglass and shape your own board. This is just like designing and implementing your own time series database. It's quite possible that you already have, as part of your tech stack, a database that works well for your time series use case. In that case, you just have to ensure that you're using your database tool correctly with the proper techniques. Later in the talk, I'll cover techniques for the proper storage and querying of time series data. Because, after all, if you don't know how to surf, even the nicest board in the world is of no use. Or maybe your team already uses a more generalized database like Postgres, and the best solution in this case might be to add a Postgres extension. This is similar to buying a new set of fins for the surfboard you already own. Fins are easily swapped out without changing the surfing experience too much. In this case, the old board is Postgres, and the new set of fins is an extension you can use with Postgres. There are several options for time series extensions you can use with Postgres. 2 of the most notable options are PG Time Series and Timescale DB. These extensions provide a user experience around creating, managing, and querying time series data, which doesn't come out of the box with vanilla Postgres. There are many benefits to extensions. Using an extension is lower lift and cheaper, plus you're already used to surfing the board. Using a Postgres extension will reduce the learning curve and augment the speed of development, while avoiding the performance hit you'd otherwise take with vanilla Postgres. A further benefit to a Postgres extension is that it will be far easier to join relational data with time series data as needed. Now that we've talked so much about Postgres extensions, you might be asking yourself what's wrong with vanilla Postgres? Why not just store my time series data in Postgres without bothering with an extension? The first reason is that these Postgres extensions come with built-in methods designed specifically for use with time series data. Without writing your own method to do so, you can, for example, query a range of data over time. More importantly, there are significant performance differences between vanilla Postgres and an extension like timescaledb. The timescaledb documentation references an experiment in which Postgres and timescaledb were tasked with ingesting a 1 billion row database. Timescaledb loads this massive database in 1/15 the total time of Postgres and sees throughput of more than 20 times that of Postgres. Because of its heavy utilization of time-space partitioning, timescaledb achieves a higher ingest rate than Postgres when dealing with large quantities of data, quantities that are quite common when dealing with time series data. Querying can be even faster. Given a query that specifies time ordering with a 100 million row table, timescaledb achieves a query latency that is 396 times faster than Postgres. Later in this presentation, when we get into the techniques such as aggregation, you'll see even more reasons for favoring a time series extension or database over vanilla Postgres. Specifically, you'll see the benefits of aggregation for data retention. And sometimes your existing tools don't cut it, and you need to invest in something entirely new. This is analogous to buying an entirely new surfboard. If you're looking for a dedicated time series database, it may be worth looking into solutions such as ClickHouse. ClickHouse pitches itself as a fast, open-source analytical database designed around time series data. Managing time series data is all about optimization, and each tool is optimized for a different ideal use case. It's essential to evaluate your conditions before selecting a surfboard. In the same way, it's important to consider what type of data you'll be working with and what you're going to be doing with it. Consensus among some users of both tools seems to be that timescaledb has a great time series story and an average data warehousing story, whereas people say that ClickHouse has a great data warehousing story and an average time series story. Look into benchmark analyses for yourself, investigate the features of each database and extension, and read up on documentation for the tool you're considering. The more you understand about the inner workings of your proposed tool, the better you'll understand how it will work with your use case. My best advice is to really get in the weeds. As a surfer, if you don't know the purpose of rocker or tail shape when selecting a board, it's going to be really difficult to make an informed decision. The same goes for understanding and selecting a solution for time series management. And sometimes no available database seems suited to your highly specific needs. If your use case is really particular and you're feeling especially industrious, you might just want to break out the foam and fiberglass and shape your own board. Meraki found itself in this situation in 2008. Our core product is a cloud-managed platform that allows users to configure and monitor their networking devices. The monitoring data is more often than not time series data. We track metrics such as packet count received by a switch, the temperature of a device, or the device's memory usage. Trends over time can give insight into the health of a system. In 2008, there were far fewer time series solutions available, so a team at Meraki developed their own. We call it LittleTable. LittleTable is a relational database optimized for time series data. LittleTable was, in fact, developed specifically for spinning disks. In 2008, storage on solid-state drives was far more expensive than storage on spinning disks, so the hardware was a significant consideration. Because of this, data is clustered for continuous disk access in order to improve performance. Later in this presentation, we'll see how this impacts the way one might design a table when using LittleTable. Fun fact, as of 2017, when the white paper was written, Meraki stored 320 terabytes of data across several hundred LittleTable servers system-wide. Now I'm sure the quantity is even higher. Though not actually a SQL database, LittleTable includes a SQL interface for querying, which has improved developer adoption by making this tool easy to use. LittleTable exists only for internal use at Meraki, but the team wrote an excellent white paper that very effectively describes the challenges and design considerations, which can be super useful for anyone trying to gain a better understanding of the intricacies of time series data. I've linked it in this slide, and I can't recommend it enough. Alrighty, we now have our board picked out. We understand the conditions we're surfing in, and we've landed on a board that works best in those conditions. However, the work is far from over. You can have the perfect board and still struggle to actually surf if you don't have the proper techniques. Technique is also incredibly important when dealing with time series data, regardless of which database tool you've chosen to use. In order to optimize performance, it's crucial that we follow some tried and true patterns for organizing and querying data. The time series techniques I'll cover in this talk are data arranged by time, composite key, querying by index, and aggregation and compression. The identifying characteristic for a time series database is that it organizes data by time for efficient access. Otherwise, it wouldn't be a time series database. Both ClickHouse and TimescaleDB will automatically generate an index on the timestamp column. This allows for the most performant access when retrieving data for a range of time. LittleTable actually clusters data on the disk by timestamp, never interleaving data with older timestamps. Because of the unique data structure, some databases enforce restrictions. Arranging data by time allows for highly efficient reads, but writing can be quite inefficient. The designers of LittleTable decided to constrain writes to be append only. Since we're collecting data over time, it doesn't make much sense to spot fill historic data anyway. According to the LittleTable white paper, there is no need to update rows, as each row represents a measurement taken at a specific point in time. When visualizing a time series database, it's important to understand that there are effectively two identifiers for a given piece of data. The first, mentioned in the previous slide, is the timestamp. The second piece of information is the identifier. In almost every case, this is comprised of multiple fields, making it a composite key. Each time series database refers to this concept using slightly different terminology. LittleTable documentation refers to this as a hierarchically delineated key, whereas ClickHouse documentation refers to this as a compound primary key, and TimescaleDB refers to this as a partition key. In order to understand the implication this composite key has on structuring data, I'm going to drill into LittleTable's hierarchically delineated key. In LittleTable, this key determines how the data is actually arranged on disk in addition to being grouped by time. This hierarchical organization enables efficient queries since it will always correspond to a contiguous region of data on the disk. It's crucial then to only query based on ordered components of this key. In order to determine the components of this key and how they're ordered, it's super important to understand how this data is going to be accessed. Your queries will only be performant if you're accessing a contiguous block of data. So you have to understand what the most common queries are going to be and design around those. It's probably best to visualize a real-world example. That way we can actually see the data arranged by these two axes, time and composite key. In this example, we can also visualize what a hierarchically delineated key in LittleTable really is. Here's an example lifted directly from the LittleTable white paper. As you can see, the data is organized along two axes. On the x-axis, we have the timestamps, and on the y-axis, we have the elements of the composite key. You'll see that along the y-axis, the records for a single network are grouped together. And within that network, all the records for a single device are grouped together. This composite key can contain as many fields as you want, thus arranging data many layers deep. In this example, though, we simply have two fields included in the composite key, grouping the data by 2 layers. As we saw in the previous example, the most important takeaway for a hierarchically delineated key is that its components are organized with an increasing degree of specificity. The example from Cisco Meraki included 2 components, network and device. Since a network has many devices, this example is purely hierarchical. However, just because the ordering in this key typically corresponds to a real-world hierarchy, it doesn't necessarily have to. You can select whatever ordering you want for the components of this key, and that ordering depends only on how the data is accessed. In our case, Liz's surfing application is designed to be surfer-specific. While we want to store data for multiple surfers, it doesn't make much sense to query data across many surfers, since each surfer is interested only in their individual progress. This means that we can prefix our primary key with the surfer so that all the data for a single surfer is co-located in the table. Then we can follow the hierarchical pattern with region and then break. The region might be, say, Los Angeles, and the break might be Malibu First Point. The region and break are very similar in concept to the example from Cisco Meraki, since a region contains many breaks. Now that we have a key that's optimized for querying, we need to actually write our queries in the most optimal way. This data is highly structured, and the way it's structured depends entirely on how we plan to query it. Hopefully you remember this graphic from a couple slides ago. This time, I've modified it to reflect the composite key we've decided on for Liz's surfing application. As a refresher, data is arranged by time across the x-axis and composite key across the y-axis. Now, for Liz's surfing application, the composite key includes surfer, region, and break in that order. In this diagram, you'll only see surfer and region, and that's because of the composite nature of the key. For the first 2 hours of last Monday, you're welcome to query for just the surfer Liz in the region LA, and you will still find a contiguous stretch of data. Now, imagine that you want to drill further and take a closer look at this green slice here. You'll see that the stretch of data is further broken down into break. Malibu exists in its own subdivided contiguous stretch of data. Hopefully this helps you visualize what your query will actually turn into. You'll see that we certainly want to include a timestamp in your where clause. After all, this is time series data. Additionally, you'll want to include part or all of the elements of that composite key. Since the data is structured hierarchically, you only ever need to include a prefix of the composite key when querying. We saw in the first example how effective a query can be for Liz in LA for the first 2 hours of last Monday. Since we've left off the break and only queried for the surfer and region, we've only queried with a prefix of the composite key. Drilling down even further, we can also query for Liz in LA in Malibu over the first 2 hours of last Monday. Or, zooming out, a query for just Liz's surfing data in that time span would also be performant. ClickHouse is a little bit different. The data in ClickHouse is not arranged across 2 dimensions. Instead, the timestamp is basically the final component of the composite key. Because of this, it doesn't make sense to include just the surfer and timestamp in the query because you're skipping the middle section of the primary key. Consider the example I've shown. We have a contiguous stretch of data for Liz, which is broken into region, which is then broken into break, which contains all of the timestamped records for, say, the last month. It doesn't make much sense to query all the data for Liz over the past 2 weeks because the data here is not contiguous. For each location, you'll have to grab just a section, skipping over the data points that don't fall within the requested time span. The only performant query for ClickHouse would be to include all the components of the primary key. You must specify the surfer, region, break, and a range of time. So it would be performant to query Liz's data for Malibu and LA over the past 2 weeks. It's important to drill down and understand how the data is arranged in your time series database of choice. By understanding the structure, you can visualize what a contiguous chunk of data looks like, and you can ensure that your query is making use of the way the data is structured. Cool. At this point, we know how to store our data and how to query it. We can now start to look at the maintenance side of things. Here's the thing. Liz surfs a lot. She plans to surf for years to come, and although we'd love to keep all of Liz's surfing data in perpetuity, we simply don't have unlimited storage space. When dealing with time series data, you have to balance 2 major concerns. You don't have unlimited storage space to keep raw data forever, but you also want to provide the user with as much data as possible. In order to solve for the first concern, the fact that we don't have unlimited storage, we need to take a look at data retention. Every time series database that I've seen includes some sort of policy for data retention. Often this comes in the form of a TTL, otherwise known as a time to live. The time to live dictates how old the data in the table is allowed to be. After a certain point, data of a certain age is simply dropped from the table. Now, we also need to address the desire to show as much data as possible. In order to do so, we need to extend the TTL without sacrificing storage. There are a few ways of going about this, notably compression and aggregation. Compression is the method of choice for the Postgres extension timescale DB. When you add data to your database, it's in the form of uncompressed rows. Timescale uses a built-in job scheduler to convert this data into the form of compressed columns. Consider the uncompressed surf data on the left. Each data point contains a single wave surfed by either of our 2 surfers, Liz and Brandon. The top right table shows this data compressed into a single data point. This preserves all of the original data while restructuring it into a format that requires less memory to store. According to Timescale DB's documentation, this can compress the size of data by as much as 90%. Additionally, you'll see that the data within this compression is ordered by timestamp. Ordering by timestamp is highly recommended in the documentation, but it's worth noting you do have to specifically configure your compression to order by timestamp. You may also be wondering about how this data gets queried. Upon querying compressed data, Timescale DB selectively uncompresses each column in order to provide the data requested. And when compressing data, Timescale stores it in column order rather than row order. We'll see more about column-based and row-based storage in the next slide. However, we can certainly be more intelligent about our compression. If there's one thing I want to harp on, it's that your database design should be driven by how you plan to query. In our case, we only ever plan to query data for a single surfer. As a result, we might want to include segmentation in our compression algorithm as well. In the bottom right table, you can see the same data segmented by surfer ID. This can certainly improve query performance. ClickHouse also uses compression to improve database performance. It may seem obvious, but less data on the disk means less I/O and faster queries and inserts. When speaking about compression in a time series context, it's important to take a couple of steps backward and talk about one of the major differences between most time series databases and a more generalized database like Postgres. This difference lies in the structure of the database, which should hopefully come as no surprise since we've already spoken at length about the importance of database structure when it comes to handling time series data. Postgres is what we call a row-based database. A row-based database organizes data by record, keeping all of the data associated with the record next to each other in memory. Row-based databases are well suited for transactional workloads where entire records need to be retrieved, updated, or inserted quickly and efficiently. With a row-based database, writing can be quite effective, but reading from large quantities of data has its shortcomings, especially when querying by a field like timestamp. And because data is grouped by record, compressing data by attribute is also quite inefficient. ClickHouse, like many time series databases, is actually a column-based database. In a column-based database, each data block stores values of a single column for multiple rows. This is ideal because compression algorithms exploit contiguous patterns of data. If this data is sorted by columns in a particular order, this can lead to incredibly efficient compression. Column-based databases are often the preferred choice for analytic and data warehousing applications. The benefits of column-based databases include faster data aggregation, high compression speeds, and less use of disk space. The drawback is that data modification is slower, but as we've discussed previously, modifying time series data is often not an intended use case. In addition to compression, there's a second approach to ensuring that we can preserve data for an extended period of time without increasing our storage costs. This approach is called aggregation, and it's the methodology of choice for Little Table. When we're speaking about aggregation, there are really two concepts, the base table and the aggregate table. The base table is where we insert the raw metrics we're recording. The aggregate tables then store a summary or average of that raw data. So first, we need to decide what raw metrics we want to store in our base table. If you recall, we already decided on a primary key that contains a surfer, region, and break. In addition, we can record metrics for each wave Liz has caught. At the most basic level, what Liz wants to know is how good was that wave? The basic stats we can record are distance and duration, so we'll include those in our base table. Then we need to know what aggregated metrics we want to record in the aggregate tables. The aggregate table will have to contain a summary of the data in the base table. It might be helpful to know the total distance summed across all waves, the total duration summed across all waves, the maximum total speed for a single wave, and the maximum number of waves caught in that time period. Now that we've decided what data to store in these aggregate tables, we'll have to decide what intervals of data make sense. These will determine which aggregate tables we want to create. This will also help us decide on our TTLs, constraining how much data we're actually using. Since Liz tends to surf at most once a day, it makes sense to aggregate data up to the day. That way, we can preserve data for each surfing session for a TTL of, say, 6 months. From there, we can also aggregate up to the week and the month, so that it's easier for Liz to track seasonal and annual trends. This leaves us with a base table with a TTL of, say, 1 month, a 1-day aggregate table with a TTL of 6 months, a 1-week aggregate table with a TTL of 1 year, and a 1-month aggregate table with a TTL of 5 years. Whew, the hardest part's over. Now that we have our data stored, aggregated, and easily accessible, we want to design an API endpoint that Liz can use to easily query her surf data. The decisions we've made when it comes to querying and aggregation will determine exactly how this API endpoint will be used. The next step is just defining an API contract which can be clearly documented for the end user, validated, and enforced. A crucial element to document for the end user is the set of allowable query params. The components and ordering of the composite key determine which query params are required and which are optional. As always, a timespan is necessary for a user querying time series data. And assuming that we're using Little Table as our underlying storage option, we only need a prefix of the primary key, so the surfer is the only required component of the key. Beyond that, you can optionally specify a region and a break. It's important, though, to document and enforce that a user must also provide a region if they want to provide a break. Recall earlier that we noted you can't skip fields in the middle of the primary key, so you must provide a full prefix of the primary key, which in this case is surfer, region, and break in that order. Now that we have the user's request, we need to determine which aggregate table we'll be querying from. This requires an understanding of some terminology. At Meraki, we discussed time series data in terms of a time span and an interval, so I'll quickly explain what we mean by each of those terms in this context. The time span describes the full period of time over which we want the data. Since our longest TTL in the database is 5 years, we can't query data for a time span that extends further than 5 years in the past. The interval corresponds to the grain at which the data is aggregated. The only options here are 1 day, 1 week, and 1 month. As noted before, each aggregation interval will be stored in its own aggregate table. We'll have a 1-day table, a 1-week table, and a 1-month table. In designing this API endpoint, we'll assume that the user wants the most data possible for the time span requested. This means that the TTL will determine which aggregate table we'll query from. We'll want to query data from the aggregate table with the smallest interval whose TTL is still greater than the time span requested. So, for example, if the user requests a time span less than or equal to 6 months, we can return daily surf data. For a time span between 6 months and 1 year, we'll return weekly surf data, and for any time span between 1 year and 5 years, we'll return monthly surf data. And we'll validate that the user is not allowed to query the API endpoint with a time span greater than 5 years, since all data is dropped after that point. Now I'd like to quickly show what a visualization might look like for time series data, now that we have in mind the concepts of a time span and interval. On this slide is another screen grab from Cisco Meraki's dashboard application. Here you can see that at the top of the page, there's a drop-down option for showing data over the past 2 hours, day, week, or month. Those are the selectable time spans. We currently have the 1-month time span selected, and in the usage graph below, you can see that the data is broken out day by day. For a 1-month time span, we're showing data over a 1-day interval. This pattern is especially useful when you want to detect trends, since trends can be found when looking at data down to the hour or over the span of an entire month. Earlier in the talk, I explained the shortcomings of Postgres when it comes to time series data. One of these shortcomings is the lack of specialized time series tooling in vanilla Postgres. Because tools like ClickHouse and TimescaleDB are so specialized for time series data, you might even be able to skip some of the steps I've listed in this Getting Out There section by leveraging some of the tools and integrations offered. ClickHouse, for instance, officially integrates with quite a few visualization tools like Grafana and Tableau. This makes quick data visualization really easy to set up. And just this year, TimescaleDB announced a project called Timescale Analytics. This initiative is not complete, and they're still receiving developer input if you're interested in commenting. What they're hoping to do is create a one-stop shop for time series analytics in Postgres. In the Timescale Analytics announcement, TimescaleDB listed a few sketching algorithms that they hope to build into this extension, which would provide data structures to estimate metrics such as percentile points and cardinality. Due to TimescaleDB's aggregation, these sketches should have very low query latency. There are so many features I haven't listed, and these products are receiving a lot of support, so I'm sure the list will grow. It'll be really cool to witness the evolution of these time series tools. Sweet. Liz now has easily accessible data on her surfing performance broken down by break over time. Fast forward several years from now, Liz has been surfing for quite some time and she's learned some important lessons. For example, she took a look at the monthly data for her favorite break and she realized that she catches far fewer waves there in the winter than she does in the summer. And the waves she does catch are way smaller and peter out quickly. It turns out that this surf spot only catches south swells, and south swells are way more common in the summertime. Liz had no idea that swell direction was seasonal. It had never occurred to her to even check. Now she knows where to surf in each season, and she's been able to update her surf routine accordingly. She's been catching way more waves, and she's been having a lot more fun. Looks like Liz is on her way to getting pitted. Thanks so much for listening. Again, I work for a remarkable company called Cisco Meraki with some of the brightest Rails developers I've ever met. I still can't believe I get to work at the intersection of web development and computer networking. It's a fascinating space to be in with really compelling problems to solve. If that sounds interesting to you, definitely swing by our booth or chat with me later. And of course, I'm always down to talk time series data. Have a great rest of your conference.